Hey, ChiSquare230. I just wanted to create a quick Muddy Points review video for the ChiSquare. Most of you haven't had a chance to fill out the Muddy Point, but given that the test is coming up, I thought I'd just create a video based on what I've gotten so far. So what I have seen are some pretty common issues. And so one here is talking about hardest thing I learned was the formulas. I had a hard time calculating frequency observed and the frequency expected. Had trouble deciding between frequency observed or expected and frequency observed, but after a while I got and a lot of concentration, I got it. So it is, oh, and then this person, the money thing for me was the second set of questions. I got confused and used the same formulas in exactly the first set, and it confused me with the wrong calculations. And then I realized what I did wrong, got 100% on the next two assignments. So let me just put it this way. So I'm going to pull up this, and I want you to recognize that this formula is the same. This is our chi-square formula, regardless of version, right? So we have two versions. We have the chi-square goodness of fit, and we have the chi-square test for independence. For both formulas, or for both versions, it's the exact same formula. Sum of frequency observed minus frequency expected, square that difference, divide it by frequency expected. So that's another E down there. So you've got frequency expected, right? And so what you need for this formula is a frequency observed for a cell, and a frequency expected for the cell. And you're going to subtract those, get the difference, square that difference, and divide it by the frequency, same frequency expected. So this is a goodness of fit version. Okay. To notice that it's a goodness of fit is you only have technically one variable. And that variable has, in this case, three different categories. So we're just going to call them A, B, and C. All right. So you'll be given in a question the frequency observed. It will have this filled in, and maybe, let's say we have maybe 10 total people, and there's 2, 5, and 3. Okay. Those, what you're given to you in the, so 2 people selected A, 5 people selected B, and 3 people selected C, right? At that point, those are your observed frequencies. So when you want to calculate the chi-square for this cell here, it's going to be 2 minus something. Then we're going to square that difference and divide by something. To get the frequency expected for the goodness of fit version, you use this formula. The proportion of what we expect in that cell times the total n. So we can see that there's an n here of 10 people total. Now, how do we get the proportion in a goodness of fit? It is based on, it depends on which version of our hypothesis we're doing. Are we doing the no difference hypothesis? In which case you should expect the same number of people in each. So one possibility is then it would be, if we did a no difference, there's 3 conditions here, then it should be a third of the people should choose A, a third should choose B, and a third should choose C. So this could end up being 1/3 times 10, which would be 3.33 repeating. And so that frequency expected would be 3.33. So this would be 2 minus 3.33333 repeating. Take that difference, square it, and divide by 3.33. Once we've done that, sum of plus, go to the next box. 5 minus the 3.33. So 5 minus 3.33, square that difference, divide by 3.33. And then finally go to the next box. Sum of, and then it'll be 3 minus 3.33 squared divided by 3.33. So that's the, so notice that these are the same. It's going to be essentially a 1 in 3 chance, right? Or a 0.33 chance. Now, it is possible though that maybe we want to do not the no difference, it's based on previous knowledge. And so we might know from previous studies and we could do an alternative where instead of using the no difference, we can say, okay, here's what we expect. We expect 25% of people to choose A, 50% to choose B, and 25% to choose C. Now notice those all add up to 1. 0.25 plus 0.5 plus 0.25 equals 1. Okay, but in that case, then our frequency expected for this first cell would be that 0.25. I want to make sure, because 25, you have to convert it to a percent or proportion, sorry. So 25% as a proportion is 0.25 times n times 10 is 2.5. So then that first cell would be 2, which is our frequency observed, minus 2.5. Get that difference, square that difference, and divide by 2.5. And then the next cell would be 0.5 times 10, or 5. And then we subtract that, and then square it and divide by 5, and so on. So this is the version that if you're doing a goodness of fit test. So make sure that you understand that that is your frequency expected. So frequency observed is easy. It's going to be given to you. Frequency expected is what you're going to have to calculate. And then for the goodness of fit, you just have to determine, are you doing a no difference hypothesis, or are you doing a previous population or something we know about it, something that we're given, and that would be given to you in the question. Otherwise, this one you just have to figure out, and they have to be equal percentages. So just take however many categories you have and do 1 divided by that. Okay, but then we've got what's called the test for independence version. Okay, now in this one, you'll notice that the difference is we have one variable up here with 3 categories, and we have a second variable that makes the rows, and it happens to have 2 categories. So if you see a box that has, again, rows, different rows, then you're doing the test for independence. Now, each of these is, again, going to have a number in it. So we might have 10, 5, 4, 1, 6, 9. Okay? Those are your observed frequencies. But then we've got to figure out the expected frequencies, and we use this version of the formula. So this is the version for the test for independence. And to do this, what we have to get are the row totals and the column totals, or the frequency for the row and the frequency for the column. So the frequency for this row right here is 10 plus 5 plus 4. So that's 19. The frequency for this is 1 plus 6 plus 9 is 16. Okay? Now we can get a total n here of 19 plus 16 is 35. Now we can do the column totals. 10 plus 1 is 11. 5 plus 6 is 11. 4 plus 9 is 13. Okay? So if I want to figure out the expected frequency for this cell, it is going to be equal to this formula, which is the column frequency, which is 11, times the row frequency. So again, there's my column frequency, 11, and there's my row frequency, 19. So 11 times 19 divided by n, 35. And so if I grab my calculator, I have 11 times 19, that equals 209 divided by 35, and I get 5.97. Okay? So, for going back to our formula up here, so as I'm calculating my chi-square, for that cell, it is going to be the observed frequency, which is 10, minus my expected frequency. So that's the frequency expected for that cell of 5.97. I'm going to square that and divide by that 5.97 again. And that part is just for that one cell. Then we've got to do it for this cell. And so let's just do one more here. So let's do it for this one. So that frequency expected is going to be, again, column total, in this case, again, 11, and again, 19 over 35. So that one is going to be also 5.97. So it would be, in this case, 5, because that's our observed frequency, minus 5.97 squared over 5.97. And then let's do the last one. This one is going to be a frequency expected, whoops, of 13 times 19 over 35. So 13 times 19 equals 247 divided by 35 is 7.05. Let's say 7.06. Okay. And so then that would be, again, plus. Now we go to the frequency observed, 4 minus the 7.06 squared over 7.06. And then we just have to continue. So you can see in this here, dot, 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 we have the top row done. Observed frequency minus the expected frequency for that cell divided by the expected frequency for that cell. So the green one is for this, the red one is for that one, the blue one is for there. Then we just have to do that second row, same thing. So just remember that this is the main point, is that you got to figure out which one you're doing, goodness of fit or test for independence, and just remember that the formula for frequency expected is different. Okay, so just make sure you have that in your notes. So that's the only thing that's different between these two. Otherwise, the chi-square is exactly the same. So that was the main part there. I think there was one other question, and it's just, what does the chi-square really represent? Is it same as the t-score, the z-score, etc., the correlation? So what I would say is it's probably the most similar to the F ratio, in the sense that a chi-square is testing how different is your data from the null hypothesis. So that's like all of them. All test statistics test that. How different is the data from my sample different from what we'd expect if there was no treatment effect or no effect? Where it's the most like an F ratio is it's that, again, skewed distribution. So you don't have two tails, you just have the one tail. And most of your chi-squares should be close to 0 or 1, right? But the bigger they get, the more difference you're getting. And that's because if you look at this, in order for a chi-square to be big, you've got to have a big difference here, meaning what you observed is different from what you expect. And so the bigger that is, the more likely you're going to get a big chi-square, and the more likely you're going to be over here in the critical region. So chi-square is just measuring how much more difference are you getting from what you'd expect if there were no treatment effect. So hopefully that helps a little bit. The main thing in terms of what the main thing that I see is that on the test is just to know those differences between the frequency expected calculations, and then otherwise just plug the numbers in for the chi-square, and then you should be okay. Okay, so that's it for the muddy points for the chi-square.